section 2.6, hard to see, it's tucked in here, but page 2. So we're doing implicit differentiation, and if you remember, the key for solving an implicit differentiation problem is that you're going to treat the y variable or the output function variable as a function of its input. So every time I take a derivative of y, or whatever variable is my output, I need to have that y prime, or maybe you write dy dx instead of y prime. So when the directions say find dy dx, it's the same thing as saying find y prime, but I'm specifically told to use implicit differentiation. This problem, I would not want to try to solve for y. It would be horrible, but even if it was a problem you could solve for y, follow the directions. So I need to take the derivative of 3x squared. I just have an x variable, and I can do that easily in my head. When I go to take the derivative of this second term, because it has an x squared that is times the y, I have to use a product rule. Same thing, that third term, it's an x times a y cubed, so I'm going to have to use a product rule, but the derivative of 2 is going to be really basic. Okay, so looking at this first one in terms of a product rule, I have a first function, x squared, whose derivative is 2x to the 1, and it's always times the second function untouched. But be careful, now when I go to take the derivative of the second function, which is just y, because it was a y, I have to put y prime, or again, maybe you put dy dx here, which is also fine. And then that's multiplied with the original second function. So in green, I've taken the product rule for what was originally the second term of the question. Now notice it was minus, so I'm putting a minus here and brackets so that I'm subtracting the whole product rule of the third term of the function. I take the derivative of x, which is 1, and multiply it with the second function untouched. Although this is a y, it was not a derivative. It was a direct copy, so I do not need y prime. Plus for a product rule, now I need the derivative of y cubed, which is 3y squared, but I took a derivative of a y. I need to write y prime, or again, if you're writing dy dx, that also works. And don't forget, we need to multiply it by the first function untouched, and we'd already talked about the equals 0. So I've taken the derivative of the parts, and if there was any little bit of math to clean up, multiplying by a 1 or rewriting it, I've got that. I distributed this negative sign to the second pink term, etc. So we had mentioned we treated y as a function of x and got y primes. So now I need to isolate or solve for those y primes by getting all of the y terms at first together on one side. Now I've highlighted my y primes, or later on I just decided to double underline them. But what happens is this 6x squared, I need to subtract it to be on the other side of the equal sign. Although there is a y in the second term, there's not a y prime, so I'm going to subtract it to the right side of the problem. But my x squared y prime is on the left. I'm going to leave it on the left of the equal sign. My minus y cubed, adding the opposite gives me a plus y cubed on the right side of the equal sign. This last term, pretty long, but it's multiplied with a y prime, so the negative 3xy squared y prime is going to stay on the left of the equal sign. So now I've got all of the y prime terms, in our case on the left side, and so now I'm ready to factor it out, right? What's in front is not like terms, so I can't just add or subtract them in this case, but I can factor that y prime out, where it's going to go outside of parentheses that just have an x squared, and it's going to go outside of parentheses where I've got my minus 3xy squared. To solve for y prime, I'm going to divide each side by whatever's multiplied with y prime. So I'm just dividing that to the right side of the function, and we're going to go ahead and leave this as is. And really, I didn't need these parentheses once I divided, but I had kind of left it for clarity and visual purposes. Okay, Again, directions say implicit differentiation. Now, it doesn't need to say to find dy dx because that's what implicit differentiation means. But I've got this problem where I have a y and an x multiplied on the left side, so I'll need a product rule. And I have an x and a y squared specifically, multiplied on the right, so I'm going to need a product rule. So I've gone ahead and broken out the parts. I'm thinking of y as my first function, and sine of x squared is my second function for the left side, x as my first function on the right side, and sine of y squared as my second function on the right side, where in every case I found all of my derivatives. If I was taking a derivative where there was a y, I had to put a y prime. I mean, right, this was 1 times y prime, but we just say y prime. I had a y squared. So, here it is. I do have the y prime on this one. And you'll notice the sine of x squared and the sine of y squared both required a chain rule. The derivative of the sine is the cosine of whatever I was taking a derivative of. But if I can further differentiate that interior piece, x squared to be 2x, I needed to do that. And then in our case, if it was a y, we needed to include the y prime. So using my product rule, which says first take f prime, which we said was y prime, multiply it with the original g that was untouched, plus for a product rule, the second function's derivative times the first function untouched, even though it's a y, it's not a derivative, so it's just a straightforward y. And then we go through the same process again. F prime was just a 1, but I need to multiply it with g, the second function untouched, plus for a product rule, g prime, which was this long old thing over here, and times this f, the original untouched function. So I had put brackets here just for clarity, but really later we're going to move this x over here, right? And there's really not much to clean up over here. But let's go ahead and go to our next step. I want to get all the y prime terms together on one side. So here's a y prime. So maybe I highlight it or double underline it. Here's a y, but it's not a prime. Here's a y, but it's not a prime. Here's a y that is a prime. So I've got these double underline symbols to let me know that this term needs to stay on the left side, whereas I need to subtract this term to the right of the equal sign. To the right of the equal sign, this term does not have a y prime, so it can stay there. It's being added on to anything that got included in that side. But on this right side, this term had a y prime, so I needed to subtract it over to the left side. There's a lot going on, but basically if I pull this y prime out, if I factor it out, I'm going to have a sine of x squared. When I factor this term out, I have the minus 2y cosine y squared, and I had just moved this x over there. So these orange parentheses are letting me know that if I distributed the y squared back, I would end up with the line above, but I can take everything in these parentheses and divide it over to the right, and you'll see this time I did not use the parentheses, and again, we're not going to simplify this any further.